Hello and good morning. It's my pleasure to deliver this presentation for the SAGE, Society of Applied Geosciences and Engineering, Benghazi International Geoscience and Engineering Conference that goes in the interval between August 30th and September 2022 in Benghazi, Libya, and online. And I'm going to make this presentation as a series, 3-in-1, about the Cyrenaican Miocene. I'll present 3 parts. The first part will be the sedimentology and sequence stratigraphy of the Cyrenaican Miocene, and then the chemostratigraphy, stable isotopes, and then the last part is the diagenesis, presented by Khalid Al-Amrouni. And here's the logos of the conference. And this is the title, Sedimentology, Stratigraphy, Chemostratigraphy, and Diagenesis of the Cyrenaican Miocene, Al-Jabal, Al-Khdar, Uplift, and Soluq, Trough, Northeast Libya. And this is these names are my team and their emails, and my team members, their emails and affiliations. The first part, sedimentology and sequence stratigraphy. I'll try to be concise and short. Of the Cyrenaican Miocene strata, Jabal Al-Khdar, Uplift, and Soluq, Trough, Northeast Libya. Here the location map. This is Libya, and this is study area, green here, Cyrenaican platform. And here the base map, we see this red line that represents the lower escarpment, which is a fold, and the upper escarpment, another fold. And the basin is surrounded here between these folds. And these yellow bars are the measured stratigraphic section in the study area. This is Benghazi city for reference, and this is the dark color is the Mediterranean Sea. So what's the objectives of this sedimentological and stratigraphic study is to document the detailed sedimentology and sequence stratigraphy of the Cyrenaican Miocene, which is called a Rajma group that includes Benghazi Formation and the Ghattara Formation and their equivalent Shledima Formation and Massus Formation. In this study, we did 29 detailed measured stratigraphic sections, and we used handheld gamma ray scintillometer profiles and carbon stable isotope variations profiles. Geological setting, Cyrenaica is part of a stable foreland basin now in the central Mediterranean region. And it has 2 major tectonic provinces, Cyrenaica platform, Al-Jabal, Al-Khdar, Uplift, and it has Marmarica Trough at the eastern side, and at the western side, Soluq Trough and Shtabia Trough. And its structure and stratigraphy is preserved, completely preserved in a unique way. About the previous study, comparing it with this current study, the previous study, they started that, or they were thinking, what's preserved in Cyrenaica is just the middle Miocene since the 1974. Up to 1990, but by 2004, there is a study by Al-Hawat et al. And Hawat up to Samad. They defined out it extends from middle to late Miocene, and they call it a Rajma group that includes Benghazi Formation and Wadi Ghattara Formation. But in this study, using more tools and carbon stable isotope, we discovered that the Miocene has a complete, the Cyrenaica platform has a complete Miocene section from early to middle to late. And we were able to correlate or extend the correlation between the Benghazi sheet at the northern side and Soluq sheet as at the southern side. And we find out Benghazi Formation extend from early to middle Miocene, and Ghattara from middle to late, and their equivalent, the Shledima Formation and Massus Formation from middle to late. So methods, sequence stratigraphy and sedimentology, we did 29 stratigraphic sections over a distance of 130 kilometers with 14 spectral gamma ray profiles with logging interval 0.5 meter and annotating panoramic digital photo mosaics. Also for the for the petrography and diagenetic studies, we studied 503 we collected 503 hand samples. We made thin section out of them. We did stable isotope analysis out of these 503 samples. And the thin sections helped us to identify the main components, cements and diagenesis. Also, we added XRF analysis for 148 samples out of these 503 samples to study the trace and common elements. So sedimentology and sequence stratigraphy, we find out this Rajma group has 9 carbonate facies and 2 siliciclastic facies deposited on a gently sloping ground. These facies deposit in 3 depositional environment, peritidal, ramp crest, and subtidal. The peritidal facies include evaporite, microbialites, palaetal facies, quartzstone and backstone, porites, they're reefs and bioplastic backstones, and quartz, sandstone, and shale tongues. And the ramp crest facies always oolitic grainstone, the subtidal facies, bioplastic facies, and reworked red algae. And reworked red algae and reworked red algae. This is the ramp evolutionary depositional model from bottom to top, early Miocene, middle Miocene, late Miocene, and from left to right, north to south. North is towards the open marine, south towards the peritidal landward direction. So the early Miocene shows by volume more red algae and bioclastics, the brownish and the blue colors. And this is towards the open marine, towards the left, but towards the right, south, there's oolitic, which is ramp crest facies, and some orange color, which is microbial facies. As we go to the middle Miocene, we see more peritidal facies, which is the green color here, the siliciclastic sand and shale tongues, with red evaporites here and microbial facies, and then evaporite again and oolitic ramp crest facies. And the volume of the bioplastics and red algae shrink it in the subtidal. As we go late, we see more peritidal microbial facies, palaetal and evaporites, oolitic, and very little bioplastic and red algae. So it shows shallowing upward as we go from early or through time from early to late Miocene, early middle late. Here, peritidal facies. This is selenitic gypsum, evaporite, A, B. Picture B is by microbial facies, E, shale, green shale, F, sandstone, fine sandstone. And here, ramp crest facies, we have cliniforms, solidic cliniforms, and this is the section for it below, A. B is oolitic grainstone with some microbial. We see fenestrol, B-salts, fenestrol porosity, and the thin section shows grapestone, oolitic grapestone. And here, subtidal facies, we have red algae with the hand sample and the field picture and thin section, intact red algae. And here, bioplastics C. You see the echinoid at the nose of the chisel, the hammer, with the thin section below to represent bioplastic features. Here we have the measured section F1, which is representative to the study area, includes 73 meters. 73 meters in thickness, and it includes 2 supersequences, SS1 and SS2, and 6 third-order sequences, plus that include 20 para sequences, shallowing upward cycles. And here we have the red curve is gamma ray. These, if we look at the lithology here, we'll find the facies change from blue and brownish, which is bioclastic and red algae open marine to oolitic and bioclastic paletal facies, which is ramp crest and lagoonal, and then to this orange color, which is microbial. So it goes from open marine, ramp crest, and then lagoonal and tidal facies upward. So it's, in general, it's shallowing upward sequence. And this is to show you the flavor or the taste of the field of view of the Cyrenaican shallowing upward cycles. We have our parasequences, PS4, PS5, PS6, those three parasequences. So for example, PS4 from this red arrow bottom to this one in the middle, it's about 4.5 to 5 meters, and it's shallowing upward cycle. And you see here oolitic and then lagoonal facies, and then oolitic and then lagoonal facies above it. And here, as we can see, the sequence stratigraphic framework of the Cyrenaican Miocene. It goes from north at the left side, which is the Al-Jabal area, all the way to south, which is Soluq Trough. And as we go from bottom to top, from old to young, there's a brownish and bluish color, which is the red algae and bioplastic facies, subtidal open marine. As we go up, you see more yellow color, which is oolitic grainstone, ramp crest facies, and then microbial facies, the orange. And then that goes to the evaporites, shifted to evaporites, and some siliciclastic tanks coming from the south of shale and sand, green and black. And then it becomes alternation of evaporite, oolitic, microbial, shallowing upward sequence. At the left side north, no siliciclastics. And here is sequence stratigraphic surface in the field. This is a sequence boundary between Eocene and the Miocene, the lower. And here the sequence boundary between early and middle Miocene. And this is the last stratigraphic surface between the middle Miocene and late Miocene, and have the maximum floodings. This is the paleogeographic maps, reconstruction of the paleogeographic maps. And as we see, it's a structurally controlled basin, controlled by two faults, the lower escarpment at the left, this line, and the upper escarpment or upper fault plain. And the basin in the middle here, see blue color bioplastic, and the brownish color is the red algae, and the dark blue, this is porites, with some oolitic yellow color at the northern side, the southern side of the basin, and some microbial at the very bottom south. This is first stage of early Miocene. In the second stage, you see more oolitic coming from north and south towards the center of the basin, and the volume of the red algae decreasing, shrinking. As we go from early to middle and late, we see more oolitic going towards the center of the basin, with the tongue of siliciclastic shale and sand coming from south to the basin, and some microbial brown color. As we go to the late, we see more oolitic and more microbial with evaporites, red ponds here, and almost the subtidal facies almost like completely disappeared, and the basin just shallowed upward. So conclusions about the sedimentology sequence stratigraphy: Rajma group, or Cyrenaican Miocene, carbonate facies deposited on a ramp setting. It has two supersequences, second order, that include 6 third order sequences, S1 to S6, and these third order sequences made up of shallowing upward cycles, meter scale shallowing upward cycles. And we noted that the early Miocene is made up mainly of red algae and bioplastics, which is open marine, associated with some porites, which is porites, their reefs. And the middle and late Miocene is dominated by microbial and oolitic grainstone facies associated with evaporites, which is ramp crest and lagoonal facies. or peritidal facies. Also, the excellent 3D exposure of the Cyrenaican Miocene made it as a good analog for oolitic greenstone reservoirs and microbial and red algae reservoirs in the subsurface within the Mediterranean and regionally and Mediterranean region and global. Now the second part, chemostratigraphy, specifically oxygen and carbon and oxygen stabilizer of the Cyrenaican Miocene. These 503 samples collected from 4 measured sections, and the sampling interval was 0.5 meter. The oxygen or delta oxygen 18 ranges from -9.2 to 3.7 per ml VP, and the carbon delta carbon 13 ranges in values from -6.7 to 3 per ml. We note that the early Miocene enriched in oxygen and carbon stabilized. The middle Miocene enriched in carbon but depleted in oxygen. Late Miocene depleted in both oxygen and carbon. So what's the objectives of this chemostratigraphic study? To determine the oxygen and carbon stable isotope curves for the Cyrenaican Miocene carbonate rocks. Also, we want to compare the regional and global Miocene oxygen and carbon curves, trends, and values with those of the Cyrenaican platform. And the carbon stable isotope will give us or provide a better age constraint on the Miocene section in the Cyrenaica. So the methods of the chemostratigraphy, we did whole rock study, samples, 503 samples with logging interval 0.5 meter, micro drilled for the oxygen and carbon stabilized study. And we used the IRMS and Kiel automated carbonate device in the stable isotope geoscience facility at Texas A&M. The carbon and oxygen stable isotope curves were plotted with a datum at the base of the maximum flooding zone in the middle Miocene. That maximum flooding zone has two criteria: high gamma ray values and positive carbon isotope excursion, which is the Monterey global. Now we did cross plots. This cross plot has for the oxygen and carbon, and the oxygen is the x-axis and carbon represent the y-axis. And these plots with age. So the Miocene has Portugalian Equitanian, early, middle Cerebellian Langian, and Langian Cerebellian, sorry, and Messenian, Tortonian Messenian is the late. So Equitanian, Portugalian, they have the most preserve the original signature. The older species preserve the original signature, while the Messenian, Tortonian, they have a lot of Diagenesis. And these squares, this is the black square, represent the global signature of the Miocene, and the Indian Ocean signature, this red square, and the blue square represent the stable isotope signature range of the Miocene in the Mediterranean. And it's very obvious our data has Diagenesis, shows inverted J. We did the same plot, but for facies, and we find out like these green triangles preserve the best signature, which is red algae facies or red algal facies, if we compare it with the other facies. Oolitic and microbial, they show a lot of Diagenesis. This is a plus sign of the circle here. So the chemostratigraphic correlation from north to south, east to west, from left to right, it shows we have the stratigraphic sections with carbon stable isotope red color curve, and the oxygen stable isotope curve plus the black curve, which is gamma ray. So each section has 3 curves and sequence stratigraphic interpretation. We built the chemosequence stratigraphic framework of the study area. Notes that high gamma ray here in the middle Miocene that associated with positive excursion of carbon and cyclastic influx, black spots here. This is the maximum flooding zone here in this Miocene section in this area. Also, we find out there are events in the Miocene sequence of Cyrenaica. For example, we did this porosity curve green, calcium weight percent magenta curve, and here we have with the red curve. This is the Cyrenaican carbon isotope, the blue curve, the Cyrenaican oxygen stable isotope curve. This red curve here, wiggly, this is Zakos, Miocene, carbon, and this blue wiggly curve, this is Zakos for the Miocene oxygen curve. So in the Cyrenaica, we find for the carbon weight percent curve, we have depletion in the calcium, sorry, for the calcium weight percent. Depletion in 3 zones, A1, A2, A3, decrease. And this decrease on the calcium is associated with increase in porosity. A1 decrease, porosity increase. A2 decrease in calcium, increase in porosity. A3 decrease in calcium, increase in porosity. And that we call them these zones, the solution zones. And some of them global, some of them local. And if we look at the carbon, we find 2 events, B1 and B2. B1 enrichment in carbon, stable isotope, that's associated with the global event, Monterey event. And B2 is Mediterranean event, depletion in the carbon, and that associated with the final emergence and exposure of the platforms. Also, if we look at the oxygen stable isotope in the middle Miocene, there is enrichment, which is local event in the Mediterranean, local evaporation. And at the end of the middle Miocene, we find depletion in the oxygen due to the complete disconnection of the Mediterranean from the Indo-Pacific Ocean. Here, there is a comparison for the main, this main magenta, this main pink colored zone. This is the Monterey event, and we're comparing this current study, Cyrenaica, with the Indian Ocean and the global Zakos curve with Europe, Malta, and Italy. And we find the same signature of the carbon excursion in the Mediterranean and globally, which is the Monterey event. Conclusions, chemostratigraphic events. Middle Miocene has highest enrichment, both oxygen and for carbon, stable isotope that coincides with Monterey carbon maximum events, and high gamma ray and siliciclastic influx. So this is for the middle Miocene. High gamma ray, high carbon excursion, and siliciclastic influx. Also, the increase in the enrichment of the carbon isotope indicates increase in carbon productivity and river runoffs. And the middle Miocene enrichment in the oxygen, the base of is local, as we said, local evaporation events, but at the top of the sequence 3, Theodore sequence, this is the disconnection of the Mediterranean from the Indo-Pacific Ocean during the survey. In the Tertonian, we saw complete depletion, or there's the most depletion in oxygen and carbon due to the progressively, progressive emergence of the platform and the shallowing upward, restricted shallowing upward. The calcium weight percent has 3 pronounced dissolution events: early Miocene, middle to late, and all these dissolution events associated with transgressive or flooding zones. There is also negative correlation between calcium carbonate and oxygen 18 values, and that's a reflection of variation in the siliciclastic influx in the middle Miocene as interpreted by John et al. 2003. And from this study, the carbon stabilized to prove that the Cyrenaican outcrops preserve a complete record of the Miocene, because we find the Monterey event in the middle of the section. That means what's below it is early and what's above it is late Miocene. Now, diagenesis of the Cyrenaican Miocene succession, Al-Jabal, Al-Khdar, Uplift, and Soluq, Trough, northeast Libya. This is the third part. So diagenesis also we did from 503 samples that collected from four sections, and the sampling interval was half a meter. Facies, this study, we studied facies based on texture, grain type, mud content, and also we studied cement, porosity types and amounts, dolomization, de-dolomization, gypsum replacement. I'd like to call it gypsification, but it's told me go gypsum replacement, silicification and recrystallization. And always we did XRF, silicon, magnesium and manganese element curves and plotting. So objectives of this diagenetic study to define the diagenetic events and processes that occur during and after the deposition of the Cyrenaican Miocene carbonate sequence, and also to establish for the first time the paragenetic sequence of the Cyrenaican Miocene carbonate strand. So these 503 samples, we made thin sections out of them, and we dyed these, we used the blue dye to identify porosity, and we used alizarin red S stain to differentiate calcite from dolomite. Calcite gets reddish color. And we'll use the potassium ferricyanide stain to distinguish ferrone versus non-ferrone carbonates. Also, we did quantitative, qualitative, and diagenetic analysis. The quantitative analysis to find the type and percentage of grains, matrix, cement, and pores. Qualitative analysis, we find out the rock texture under the microscope, fabric and grain size, sedimentary structures, primary and secondary, and trace fossils. For the diagenetic process, we studied micronization, dissolution, leaching, which is for pores or porosity, pores creating porosity, and then cementation, which is pores destruction, and then compaction, mechanical and chemical, and neomorphism that shows recrystallization, inversion, and replacement, etc. These are the methods. So Cyrenaican Miocene paragenetic sequence shows 18 events, but basically we can summarize them in two main events: porosity creation and porosity destruction. The blue ones, porosity creation, which is 7 events, and porosity creation made by dissolution and fracturing, and porosity destruction made by cementation, basically. And here, all the diagenetic processes, and there are 18 of them in this study. Symmetrical rim and pore filling cement. Here we have rim cement, fibrous, and here we have another type of rim cement, and here we have pore filling between the grains. And this is zoom in B to show the pore filling. And now here this showing the types of oomoldic porosity in this A, and here biomoldic porosity in B, and here show fracture filled with silica. And in this one, which shows crust cement and fan-shaped cement. When these fans coalesce, we call petroidal cement, and usually go with refill facies. Also, we have silica replacing gypsum. This crystal of gypsum replaced by silica completely. And here we have oolitic facies fractured and replaced by silica, and some fractures filled with silica. Here we have compaction style, solution seams. And here we have dolomite, and we have this dolomite becomes dedolomatize it and becomes calcite. And alizarin red S shows us still have pseudoform, the wrong shape, but the red ones are calcitized, dedolomatized. This is the usage of XRF in association with the porosity and the stratigraphic log. This is the silicon curve, Si, and magnesium curve, and manganese curve. Manganese almost zero until we pass the maximum flooding surface, which shows a lot of manganese here, indicates fresh water, and the magnesium indicates like marine. And as you go up close to the fresh, it disappears. And here we have the silicon, which shows some spikes along the stratigraphic surfaces. And as we have high porosity zones, the silicon disappears. Same thing here, same thing here. Also notes the magnesium and the dolomite here. There's dolomite associated hand in hand, where magnesium disappeared, dolomite disappeared. And again, this is the paragenetic sequence of Cyrenaica that we summarized by the porosity creation zones, the blue ones, and that's represented by the dissolution and fracturing, and the rest is cementation zones, which is porosity blocking. The conclusion of petrographic and diagenesis. Petrography and diagenesis, we have two distinct lithologies. The lithological, textural, and paragenetic events above and below the sequence boundary corresponding roughly to the middle Miocene, Langia-cerebellum boundary. Okay, what's about that distinction? Older Miocene interval is dominated by silicified, dedolomatized, bioclastic-rich bryozoan, red algae, backstone beds. So it has silicification and dedolomatization. Younger Miocene sequence dominated by silicified and recrystallized oolitic grainstone, microbial, bioclastic, oolitic grainstone. So the top one, the older one silicified, dedolomatized, and the younger one silicified and recrystallized. And the paragenetic sequence shows 18 diagenetic events in a shallow setting, so never been buried. The Miocene sequence, Cyrenaican Miocene sequence, never been buried. And the late Miocene has the lowest average porosity value, where the middle Miocene has the highest average porosity value, and the early Miocene, very old, has the medial average porosity. The silicon, magnesium, and manganese element curves from the XRF have three different patterns. The silicon shows spike increase at some third order sequence boundaries above some timelines between Miocene ages. The magnesium curve is continuous throughout the dolomatized lower part of the Miocene. The manganese element occurred only in the upper part of the Miocene, where we have freshwater diagenesis. Recap: the Cyrenaican Miocene has two second-order super sequences, and 6 third-order sequences and 20 parasequences. Chemostratigraphy, too. Chemostratigraphy can be correlated regionally and globally, and age more complete than previously thought in the Cyrenaican Miocene. Even with partially resetting of carbon and oxygen, record events can be correlated. Diagenesis is mainly shallow marine events, cementation, dissolution, since never been buried deeply for the Cyrenaican Miocene. And thank you very much for your time, and I'm ready for any questions. Thank you.